Okay, let's talk about antiderivatives. First of all, the reverse of finding a derivative is known as antidifferentiation. Let's write down a definition. We're going to say a function f, call it capital F, is an antiderivative of a function, it's called little f, if I can take the derivative of capital F, so capital F prime of x, and get back our function little f. Let's see what I mean as far as an example. Let's say capital F of x is defined as the function x cubed over 3. This is indeed the antiderivative of, let's say, f of x, little f of x, is equal to x squared. I mean, you can check it. I could say, well, if capital F of x is defined, in this case, as x cubed over 3, or I can write that as 1/3 times x cubed, then the derivative of capital F, let's note it as capital F prime of x, is equal to what? Well, my power rule says I will multiply the 3 times the 1/3 and reduce the power by 1. So we would have x squared, which is indeed f of x, little f of x, right? So I've just shown that capital F of x is the antiderivative by definition of little f of x. But I want you to notice that there's more than one antiderivative for a function. So I'm going to write that down. There's more than one antiderivative for a function. And I'm going to put exclamation points on that. For example, what if I call capital F of x 1/3 x cubed, but then I have plus 2? Well, let's take the derivative of that. Let's go ahead and say, let's apply the derivative. So let's say I'm going to take the derivative of this function, capital F, and what am I going to get? 3 times 1/3 is going to be 1. Reduce the power by 1, I get x squared, and the derivative of 2 is 0. And look again, I have now gotten back the function little f of x. So look, this capital F of x is also an antiderivative for the function x squared. So in general, we can just say that these will differ, the antiderivative, will differ by a constant. So let's go ahead and write that. Let's do it for this case in particular. In general, the antiderivative of the function f of x equals x squared can be written, I could call it capital F of x, but it can be written as x cubed over 3 plus a constant, right? This case is the same as 1/3 x cubed plus 2, which is also the same up here where I can make this constant 0. So we can see we've got a whole family of antiderivatives. So it's important to have this plus c, or the constant. They differ by a constant. Okay, so now we have an idea of the definition of an antiderivative. Let's just get some notation things down. So what I'm going to introduce to you now is called the indefinite integral. And we use this symbol, it's called the integrand. To denote that we're going to find the antiderivative. So I'm going to put a function here, let's call it f of x. Oops, I don't know why I said that. It's called the integral symbol. I just noticed that as I'm about to write the next part. This is the integral symbol. That was silly. This is called the integrand. That's why I noticed I said it funny. And then it's like a sentence in English that has to be complete. I'm going to have this integral symbol. I'm going to have the integrand, which tells me the function that I am finding the antiderivative of, and then this dx or dy or dt, whatever is back here, tells you that what anti-differentiation is performed with respect to. So this in particular, where it says dx, it says that the anti-differentiation is performed with respect to x. So this could have had dy, and that would be anti-differentiation performed with respect to y. This represents the family of all antiderivatives, and so using that last example, let's just put things into play here. I've got the integral of x squared dx. So this tells me when I look at it that I'm finding the antiderivative of x squared with respect to x, and I now know that the answer is going to be x cubed over 3, and I would put a plus c. So if I go from this left-hand side to the right-hand side, this is called anti-differentiation. So from left to right, this is anti-differentiation. And if I want to go from the right side to the left, this is called differentiation, which we have done all semester. Okay, pretty much for the most part of the semester we've been talking about finding derivatives, and we had a set of rules, and if we could use those rules or manipulate something in a way that we could use the rules, that's what we would do to find the derivative. So likewise, we are now going to have formulas for basic functions is what I'll call them, but this time we're talking about anti-differentiation. So formulas for basic functions. Okay, we're going to use c to represent a constant, just as we spoke about before. Okay, our first basic rule will be if you see an integral and it has x raised to some power, let's call it n, and it tells you to find the antiderivative with respect to x, well, we're going backwards now. So we're not taking the derivative. Before, when we took the derivative, we would multiply and subtract power by 1. We're going the other way. So you could probably imagine it makes sense. I'm going to rewrite this base x. I'm going to add 1 to the exponent. And instead of multiplying by that, as we do with the power rule, we're now going to divide by it. Right? So if I look back at this example here, if I have x squared, I'm going to add 1 to the power, so that makes it cubed, and then I'm going to divide by that power. And then we have plus the constant because we were talking about the indefinite integral here. Okay, so basic example, you just saw it a second ago. I could also go a little bit further, put x to the 4th dx, and if I tell you to find the antiderivative, you would go, oh, all I have to do is add 1 to the power, divide by it, and don't forget to add my constant. Another way that you'll see this written is, as I did before, you could put that 1/5 off to the side there, and that would be the same thing. Okay, either is acceptable. Now let's look at the next basic example. We've worked with taking derivatives of exponentials. So here we are with the antiderivative of e to the x dx, so the integral of e to the x dx. Well, you should know that the derivative of e to the x was itself. So in that sense, it's also going to be the antiderivative, right? You could check this. You should be able to check from the right hand to the left. If I take the derivative of the right hand, I should get this integrand. And so we could very easily check that out. Okay, the next thing that might occur if we're going down our list of basic functions is what if I have e to the kx dx. So here I have that k is going to be a multiplier, and all I would do in this sense is I would take 1 over k, rewrite my e to the kx, and then I have to add my constant. And again, you should be able to check this very nicely and easily. So if I have the integral of e to the 5x dx, I'm asked to find the antiderivative or look at this problem and solve it. I'm going to do exactly as this rule says. This 5 is like my k, so I'd have 1/5, and then I would rewrite my e to the 5x, and then I'd have my plus the constant. And you can very easily take the derivative of the right-hand side, right? This is using chain rule, and I would get back to e to the 5x if I took the derivative. Okay, so all those good derivative rules from before, we can go back and use those to check. Right now we're getting our feet wet into finding antiderivatives, so just some basic rules again. Here I am looking at the integral of a to the x dx. Well, a is going to be our base here. It should make sense when I write down. I'll have 1 over the natural log of that base. We called it a here. You'll multiply it by a to the x, and you'll write down plus c. So remember, if I took the derivative of the right-hand side, I should get this back at a to the x. And you can verify from everything that we've done previously with our derivative rules, with exponentials and logs, these very much will make sense. And so now let's kind of change this up a little bit. I'm going to change the color here. Let's put a k, saying that I have a multiplier there in front of that exponent. And so likewise, I would have 1 over, I would have my k, so perhaps I should make this blue, 1 over my k, natural log of the base, which I called a, multiplied by a to the kx, so you just rewrite it, and then you have your plus the constant c. Okay, so let's see that one in action. If I were given the integral of 5 raised to the 3x dx, and notice it's like a complete sentence here, I'm asked to work on this. I will go, oh, I have a multiplier, it's like my k, you see me circling that. I don't know why I have that there. Just erase that. Once you take the antiderivative, this integral symbol is no longer there. Okay, so I'm going to have 1 over my k, which is 3. I'll multiply by the natural log of the base, which is 5, and then you will rewrite that 5 raised to the 3x. And of course, this is the family of antiderivatives. I've got an indefinite integral. I'm going to have the plus the constant. Okay, and really the last basic function that we take the antiderivative of would be, what about if I have 1 over x dx? Okay, let's dig back and think about our derivatives of logarithms. What was the derivative of natural log of x? Well, it was 1 over x. So here this is going to be the derivative, the antiderivative is going to be the natural log of the absolute value of x plus c. Okay, and we'll see this coming up rather quickly in some examples in our homework. And so hopefully you practice with these enough, since we've spent so much time going really from the right-hand side to the left. This should become fairly easy for you. You'll start seeing the patterns and recognizing them. A few things just to put in as far as properties. So back when we were talking about limits, perhaps at the beginning of the semester, we discussed how limits, you would be able to take it apart. You can add and subtract and break that up and perform the limit operations, these properties of limits. And so likewise, we have these properties of the integrals, or the antiderivatives. And this allows us to make something look pretty complicated into something easier to work with. So the first property would be, if you see a constant k and you recognize a function behind it, so k is being multiplied. So let's say this was like 5x squared. 5 would be like your k. What you can actually do is move that k in front of the integral. And so what this means for you is that you can work on taking the antiderivative of the function f of x and then multiply it by k. So this actually will save you some time and help you rewrite things. We can also continue and say, well, what if I have 2 functions here? And maybe it's like x squared plus 9x. So I can think of x squared as the first function, 9x as the second function. So if I have a plus or minus in between here, this property says that what I could actually do is break this apart, and I can work with taking the antiderivative of the function f, and then I can add or subtract according to whatever is given to me with the antiderivative of that next function. Right? And I can do this over and over again for as many functions as I'm dealing with. Okay, one other thing, it's not really a property, but it's important to note here. So if I just have a number here, let's call it k, a constant, what's really sitting here, it's k times x to the 0, isn't it? X to the 0 is 1, so I don't have to write that 1 here. But I want you to think about, you're taking an antiderivative, and this is following that basic like anti-power rule, right? Where you look at this and you say, I'm going to add 1, and I'm going to divide by it. So actually, let's go ahead and invoke that we'll put the k on the outside. I'll break it up into several parts here. So I'm now saying I'm going to put the k on the outside, and I'm going to take the antiderivative of x to the 0. Well, I add 1, so x to the first, and I divide by it. And then I need the constant. So what you actually have is that the answer is kx plus c. So I just want you to keep that in mind. Okay. Save some space over here. Let's make it like 4 dx. I'm taking the antiderivative of 4 dx. So I can rewrite this as 4 times the integral of 1 dx, right? And so I would be able to say this is just 4x plus the constant is my answer. Okay, let's get into using these properties. And so we're going to find the indefinite integral. I'll say the first example will be the integral of 9e to the x dx. And so I'm finding the indefinite integral, and I'm going to use the properties to go ahead and rewrite this so that my 9 is hanging out on the other side of that integral symbol. And that constant is just going to hang out, so it's going to be 9 times whatever the antiderivative is here. Well, we just discussed that the antiderivative of e to the x is itself. However, I need to have that constant. And so I would write this as 9e to the x plus c. Okay. Moving to the next one, let's take a look at what 5 times t to the 7th plus 1 over t dt, what its antiderivative would look like. And if you want, you can say, well, I've got two functions here, so let's deal with it as two different integrals, and that's fine. You could also say, hey, I choose to put that 5 in the front. Okay, we can do that. It really isn't necessary. Sometimes it's more to our benefit. So you could do that or not. I'm not going to do it in this case. But now I'm using this, I'm going to call it anti-power rule for lack of a better term. But I recognize that I am adding 1 to that exponent and dividing by it. So 7 plus 1 is 8. That 5 is going to hang out. So now I have t to the 8th. And I am going to divide by that new power, which is 8. And I can write it simply as 5/8 times t to the 8th. I would have a constant from here, wouldn't I? And now I move over here, and I'm going to take the antiderivative of 1 over t. And this is where I need to realize that, oh yeah, 1 over t, its antiderivative is the natural log of the absolute value of t. I took an antiderivative, indefinite one, it was plus c. So take a look, I've got a constant. I don't know what this constant is yet. I don't have an initial value problem. I don't have bounds, as we'll get into later. But a constant plus a constant is just another constant. So I can actually combine this as a single plus a constant. And this is absolutely a fine answer to work with. That looks great. Let's take a look at one more using these properties. Maybe two more. Let's do the antiderivative of 4 times the 5th root of w cubed minus 3 over w to the 4th plus 5, and I'm finding the antiderivative with respect to w. Okay, So we can break this up into the various parts. I can move the 4 on the outside here, and then I'm already thinking to rewrite this as w to the 3/5. Then I've got another integral. I can move the 3 to the outside, and so that I have 1 over w to the 4th. And you know what? We're smart enough now that I know I could use those negative exponents. So let's make this w to the negative 4th. And then I have the antiderivative of 5. And so I could put the 5 here, move it out, dw. So these are all the little pieces I'm looking at and taking the antiderivative of. Notice that I'm being very careful in rewriting this so I can use my rules. And these are all things that we've been doing all semester. So as I come through, I'm going to add 1 and divide by that exponent. So that 4 is going to come down. It's just a constant. I add 1 in the form of 5 over 5. That's the same thing as 1. So if I add 5/5 to 3/5, I now have 8/5. So I'm going to have w to the 8/5. And you're supposed to divide by 8/5. I'll rewrite that in a moment. I have a constant, but I'm going to save that till the very end. Over here I have minus 3 times w to the, add 1 to the power is negative 3. Divide by that new power, negative 3. So you can see I'm going to have to do a little bit of simplifying. And then I move over to the next part here. The antiderivative of 5 is going to be 5w. I add 1 to the exponent and then divide by it. And then I have my constant. So let's go back and make this look a little bit nicer. Notice that dividing by 8/5 is the same thing as multiplying by the reciprocal of 8/5. So this is going to be 4 times the reciprocal of that, which is 5/8, times w to the 8/5. So I'm still going to have a little bit more to do. I have a plus sign here. A negative 3 over negative 3 is a positive 1, plus w to the negative 3, plus 5w, plus my constant. And then the last thing that I'm going to do is just clean up right here. This is 4 over 1, right? And so I'm going to have, once this is simplified, 5/2 w to the 8/5 plus w to the negative 3 plus 5w plus c. Now there's a few things I can do here, such as move this back into radical form and then get rid of my negative exponent. But I think this does justice to what we're trying to accomplish here. Okay, let's do one more. Let's say I'm given this rational expression that I'm to find the antiderivative of. So I've got x to the 4th minus 8w cubed all over x squared. Haven't learned any rules about this yet, but part of what we've done in the beginning of the semester is say if I can't see a rule to use immediately, what can I do to rewrite this so that I can use a rule? Well, think about this. This really is just, it's a fraction, right? It's an expression with a common denominator. So why not break this up and simplify it? I don't know why I have w's and x's. This is supposed to be a, should have caught that. That was supposed to be an x cubed. Okay, so pause it, go back, erase it. But I'm going to break this up so that I can simplify it and then use my rules. So I have everything in terms of x. I've got my antiderivative of now x squared minus 8x, right? That's after I simplify using my rules of exponents. And so I'm going to add 1 and divide by these terms. So if I add 1 to 2, that'd be cubed. I divide by 3, or that's the same thing as multiplying by 1/3. I'll move over to the next one. I'll have a minus sign. I add 1 to the existing exponent, which is 1. So 1 plus 1 is 2. And if I divide 8 by 2, I get 4. And then I have the plus the constant. Okay. So I added 1 and divided, and I went ahead and showed that result without showing that intermediate step. Okay, the last thing to note in this section where we introduce antiderivatives would be anytime before when we're talking about application problems and we would discuss what marginal meant. So if we're talking about a cost function, I said find the marginal cost function. If you saw the word marginal, you should have thought, or triggered at least in your head, take the derivative. So now you may be given the marginal cost function and you want to go back to the cost function. So if you see marginal, that still indicates something with a derivative. If you want to go back to the original function, you're finding the antiderivative. So that's really how you're going to use this application. So we could talk about marginal revenue, going back to the revenue function, so find the antiderivative, or we could talk about the marginal profit function, and you want to go back to the profit function, you would take the antiderivative.